This is an introduction to transistors, and what we do in this chapter is I'm going to try to skip the physics and concentrate on some practical problems. Earlier, we saw that there are two types of semiconductor material, the P and the N type, and that when they are combined, we create a new device called a diode. And the diode has an anode and a cathode, and the diode conducts conventional current in only one direction. Now we will do the same thing, except we're going to have three layers of material, N, P, N. Notice then that we have actually two diodes, one diode pointing down and the other one pointing up. Now we have three terminals, which we will label the base, the collector, and the emitter. Now the concept is that if we put a very small current into the base, this small current will cause the diode that points upwards to reverse, and in doing so, it'll create a larger current to flow through the collector down to the emitter, and that both currents will combine to form emitter current. Then the trick is how to turn on the transistor, which is called how to bias the transistor, and how to put it to use. Here we have created a practical circuit for the transistor. Notice that we have a resistor into the base and another resistor into the collector. What we're trying to do is to create a path for current into the base and one for the collector. But notice that there's a switch connected with the base circuit. That means that at this moment, if you look at it, there is no current flowing into the base. If there is no current flowing into the base, that means that the transistor is off. We call this cutoff. And in cutoff, there is no current into the base, therefore no current in the collector. And then if we take a voltmeter and measure the voltage at the collector with respect to ground, we would find that the voltage would be 15 volts, or otherwise source voltage. Here is the same circuit, but notice that now we have closed the switch, which means now we will have current into the base, which will not cause current through the collector, and both will combine with current into the emitter. This is called the active region. The true definition of the active region is that we have base current, which causes collector current, and then if we measure the voltage at the collector with respect to the emitter, we should get a positive number, but not zero. And then also, if we measure the voltage at the collector with respect to the base, we also get a positive number, which indicates that the diode that points upward has reversed. There are times when we might have base current and collector current, but if we pick the wrong resistors, that too much collector current can flow. In that case, this is called saturation. In saturation, if we measure the voltage between the collector and the emitter, we will find 0 volts. That means that all the source voltage has been dropped across the collector resistor, and this is called saturation, but we don't know if we're in saturation until we do more calculations. Let's try looking at a more practical problem. And notice right away, underneath the schematic diagram, it says that beta equals 200. Beta must be given to you by the manufacturer in their data sheets, and beta is the ratio of collector current to base current, which we'll be using in just a moment. Let's begin by calculating the base current. We have a source of 2 volts, that's called VBB, and then we subtract zero point 0.7 volts. Why? Because we have a diode in the current path. The lower part of the transistor is a diode. So now we say 2 volts minus zero point 0.7 volts divided by the base resistor, 100 kilo ohms. The base current is 13 microamps. Now we use beta to calculate the collector current. Since beta is collector current divided by base current, then collector current is equal to beta times base current. In other words, 200 times 13 microamps, which equals 2.6 milliamps. The collector current will cause a voltage drop across the collector resistor, and this is called VRC, and it equals collector current times the resistor value. In other words, 2.6 milliamps times 1 kilo ohm, which equals 2.6 volts. We calculate the voltage at the collector VC by saying that it is VCC minus VRC, or 10 volts minus 2.6 volts. So VC is equal to 7.4 volts. In this circuit, the emitter is attached to ground. But even so, we say that VCE is equal to VC minus VE. In other words, 7.4 volts minus 0 volts, and this equals 7.4 volts. Notice then that VCE is the positive number that we were looking for, and what this does is it proves that this transistor circuit is an active transistor. Once again, read all the chapter and look at the physics, but try to concentrate on the practical problems and not so much the physics behind the transistors.